Programming Quadruped Robot to walk using ROS2 and Gazebo. Crawl gait example. Outline. In this presentation, technical task of programming robot dog to walk is considered. Presentation contains brief description of Quadruped Robot model in Gazebo, explanation of ROS2 forward command controller usage for robot programming, 3 robot walking programs, realizing crawl gait and explanation of the programs. Quadruped Robot model in Gazebo. Robot model is defined in Gazebo, a free open-source robot simulation environment. Gazebo offers physics simulation at high degree of fidelity. You must have Gazebo installed on your computer. Please refer to Gazebo official page for installation process explanation. Except for having Gazebo installed, you do not need any experience of running Gazebo. Note that programs offered in this presentation were developed using Gazebo Harmonic v8.8. Usage of ROS2 for robot simulation. The robot operating system ROS2 is a set of software libraries and tools that helps in building robot applications. Robot walk programs were developed using Ubuntu 24.04 LTS system and ROS-JZ. Note that these programs were not tried for other versions or releases of operating system and ROS2. ROS2 offers forward command controller for a set of joints. This class forwards the command signal down to a set of joints on the specified interface. Forward command controller is defined in the robot controller YAML file placed in the directory shown on this page. For position controlled joints, desired positions are simply forwarded to the joints. Content of robot controller YAML file is shown in the next page. Robot control YAML file describes the robot dog joint structure. File contains list of all dog's joints. It also specifies names of position controller and state broadcaster. Robot dog joint structure. Quadruped robot model possesses leg, thigh and shin joints. As shown in the drawing on the previous page, leg joint is used to attach the thigh to the robot body. We set leg joint angle to 0 and do not change it during simulation. This is because in this presentation we realize the simplest way of walk, crawl gait without turns. For crawl gait, at any moment in time, 3 legs of the robot touch the ground, providing better stability compared to other gaits, such as trot or gallop. To realize other gaits and turns in subsequent videos, leg angles will be changed too. Forwarding joints positions using ROS2 publisher. In the developed programs, in order to forward desired angle values to the joints, a publisher is defined using standard ROS2 command. The command says that forward position controller publishes data in float64 multi-array format. Since ROS2 publisher requires data in float64 multi-array format, leg angle data which are stored in array named action1 transform to float64 multi-array format using the following statement. Then desired angles of robot joints are published as self-publisher publish angles array. Next, explanation how to prepare the angles array named array 1 follows. Angle array structure. Joint angles are described in angle array in the following order: front right leg, thigh shin; front left leg, thigh shin; rear right leg, thigh shin; rear left leg, thigh shin. Total number of elements in the angle array is 12. However, since all leg joint angles are set to 0, only 8 angle values must be specified. Simulating robot steps. In this presentation, 3 approaches to robot walk simulation were tried and 3 simulation programs were developed. In Walk 1 and Walk 2 programs, numerical simulation steps are counted and values for joint angles are specified depending on simulation step number. Robot steps are decomposed into a number of elemental moves. Such moves may be, for example, raising the robot's leg above the ground, stretching the leg on a certain height above the ground, changing leg height above the ground, and so on. Duration of each elemental move may vary depending on a move. For example, raising or putting down a leg may be fast, while stretching a leg over the ground may take longer time. In Walk 1 program, duration of elemental move is determined by the number of simulation steps allocated for the move. In this program, short simulation step of 20 milliseconds was used and number of steps for elemental move simulation varied from 5 to 50. Number of elemental moves for robot step varied from 2 to 7 depending on robot leg. The number of elemental moves was increased if it was deemed that current step was not satisfactory. Therefore, steps with large and small number of elemental moves coexist in the programs. Program's description. Main target pursued in the developed programs was achieving as large robot step as possible. For all 3 programs, in the initial position from which simulation proceeds, angles of all side joints are set to 0.3 radians and angles of all shin joints to minus 0.4 radians. Robot takes initial position in the first moments of simulation. Then, if side joint angle is set larger than 0.3 radians, robot will move its leg forward. If side joint angle is set less than 0.3 radians, robot will move its leg backwards. When robot leg is moving forward, shin also must be extended forward. This is achieved by setting shin joint angle less than minus 0.4 radians. Determining angle values. Angle values for thigh and shin joints were determined by trial and error method. Joint angles were ascertained as the largest values for which robot still could keep its balance without falling. Additional problem was that for large back leg steps forward, robot tended to fall backwards. We figured out that this problem can be partially alleviated by lowering down front part of robot body by bending down its front legs, or specifically making the angle between thigh and shin joints smaller while keeping thigh joint angle large. It is very important that when robot moves one of its legs forward, other legs push backwards. This is realized by decreasing thigh angle while keeping robot legs on the ground. Note that this is different from the step backwards, since when robot makes a step, it raises its leg above the ground. Without push backwards, robot will not make good advance even when making large forward steps. In addition, at the final stage of the forward step, robot needs to put its leg down gently, otherwise it can slide backwards instead of moving forward. Since robot leg is put on the ground by decreasing or making more negative shin joint angle decreased should not be abrupt. Running Walk 1 program. Walk 1 program and files required to run Gazebo and ROS2 are stored in a folder named Quadruped Robot Walk 1. Download the program using links available in the description on this video. After download, Quadruped Robot Walk 1 folder contains only one folder named SRC. Open terminal window and move to Quadruped Robot Walk 1 folder. Execute /build command. 3 new folders named build, install and log will appear alongside the SRC folder. Next, open second terminal window, move to Quadruped Robot Walk 1 folder and execute the following command: source install setup bash. Then execute the following command: ROS2 launch robot Gazebo main launch py. Gazebo simulator will be launched. Open third terminal window, execute the source command, and then execute run command: ROS2 run robot control walk 1 py. Robot will start moving. Example of walk 1 program execution. After executing run command in the third terminal window, robot will briefly assume the initial pose discussed on page 11 and then will start walking, firstly moving right back leg forward, then right front leg forward, then left back leg forward, and then left front leg forward. This sequence of 4 leg steps is repeated several times, employing 1250 simulation steps of 20 milliseconds duration. Total walk time for 1250 simulation steps is 25 seconds. To provide more time for observation, simulation sequence of 1250 simulation steps is repeated in walk 1 program once again using for loop. After the command in the second terminal window is executed, Gazebo is launched, and you will see robot standing at the right side of the Gazebo plane. Third terminal window is placed in the upper right side of the Gazebo window. After run command in the third terminal window is executed, robot briefly assumes initial pose and then starts walking. Robot tries to extend his front legs as far as possible. It also lowers its front part of the body to enable larger step by back legs. As was discussed previously, in walk 1 program, robot repeats same walking sequence twice. Okay, now walk 1 program execution is completed, and we exit from walk1 program using exit statement. So Python prints runtime error, saying that it cannot continue after shutdown. So shutdown was our intention, and you can ignore such runtime error. So we can run walk1 program once again. However, since robot, if it will continue walking, will escape from our view, it's good to adjust its position. You can do it using your mouse. And also you can adjust size of the robot by rotating scroll wheel in the middle of your mouse. For example, make it a little bit smaller. So now walk1 program will be executed once again. So first part of the walking sequence is completed, and robot repeats it once again. You can adjust robot size while it's walking. For example, make it smaller. Of course, make it larger. Also, you can adjust position of the robot even while it is walking. Okay, so now execution of walk1 program is completed. walk1 Py source code is stored in src robot control scripts folder. Those who would like to modify or improve walk1 program need to change angle values in the angle array named action1. Comments are available. Do not forget to execute calconbuild command after each program modification. In walk1 program, duration of elemental moves can be fine-tuned using different number of simulation steps for different moves. Such an approach provides great flexibility for robot-like movement design. In walk2 program, each elemental move is simulated using only one step. In this way, number of simulation steps programmer needs to specify is reduced. In walk2 program, duration of simulation step is increased to 0.35 seconds compared to 0.02 seconds in walk1 program. This is because sufficient time has to be allocated for completing the move in one step. In the programs, simulation step duration is defined using time delta variable. Walking sequence using 210 simulation steps is developed in walk2 program. Robot walking time is 1 minute and 14 seconds. Number of simulation steps is reduced and robot walking time is increased compared to walk1 program. walk2 source code is stored in src robot control scripts folder. In order to support effort of those who would like to modify the program, comments are provided. Now, simulation results for ROS2 program will be demonstrated. Similar to ROS1 program, after run command in the set terminal window is executed, robot briefly assumes the initial pose and then starts moving forward. In ROS2 program, simplified approach to robot step modeling is employed. Duration of elemental moves in ROS2 program differs from duration of elemental moves in ROS1 program. However, decomposition of robot steps into elemental moves is same to ROS1 program. I want to run ROS2 program again, however, adjusting of robot position is necessary. To prevent robot from escaping from our view, I will change size of robot a little bit. Make it smaller. Okay, so now run command will be executed again. So also ROS2 program uses simplified approach to robot step modeling. We can say that it produces good work and it's a viable approach. So now robot already has no chance of escaping from our view, so I will make its size a little bit larger. Okay, demonstration of ROS2 program is finished. In ROS3 program, compact and simple walking program is developed. Decomposition of robot steps into elemental moves employed in ROS1 and ROS2 programs is abandoned, and robot step is performed in just one simulation step. Therefore, robot leg move in this program is very simple. Robot slightly raises its leg above the ground, stretches it and lands it on the ground again. A leg number counter named leg is introduced. Leg equal 1 denotes right back leg move. leg equal 2 denotes right front leg move, leg equals 3 denotes left back leg move, and leg equal 4 denotes left front leg move. Same as in walk 1 and walk 2 programs, robot starts walking moving forwards its right back leg. At each simulation step, value of leg is increased by 1. After reaching 4, value of leg counter is reset to 1. A set of angle values is assigned for each value of leg counter. These angle values were determined based on analysis of walk 1 and walk 2 simulation results. Only 4 sets of angles are used in walk 3 program. Program part describing walking sequence contains just a dozen of lines. In walk 3 program, duration of simulation step is increased to 0.7 seconds compared to 0.35 seconds in walk 2 program to provide sufficient time for completing robot leg movement just in one simulation step. Note that simulation step duration depends on CPU speed. You may want to decrease or increase simulation step duration if you use very fast or slow CPU by modifying value of time delta variable. Robot walk in walk 3 program can be modified by changing shin and thigh angle values in the angle array named action. Then angle array action 1 will be generated and submitted to the publisher. Now results for walk 3 program will be demonstrated. As in previous examples, robot briefly assumes initial pose and then starts moving forward. Robot moves stretching its legs just above the ground. This is because in walk 3 program a simplified approach is used. Each step is performed just in one move, and therefore angles we specify in this program must be the angles robot assumes at the final moments of each step, and as a result robot just stretches its legs just above the ground. I will move on. Okay, so execution of program is completed, and I will run it once again. Okay, so now robot continues its walk. So we also can see that when robot lands its leg on the ground, it slightly tilts its body. In walk 1 and walk 2 programs, we landed robot legs at the end of the step by making more negative shin angle. But here, because we complete step just in one move, we cannot change angles during walk, so robot lands its leg on the ground by using its body. Okay, so walking sequence is completed again, and I will run the program once again. In Walk3 program, number of steps robot will accomplish is determined by a loop. So now it's 160 steps, but it's possible to increase it, and then robot will walk quite a long time. So now robot steps do not resemble steps of a real dog, but robot vigorously moves forward, and if number of steps in the loop will be increased, robot can walk rather large distance. So now it's again is trying to escape from our view. So okay, walking sequence is completed third time, and this brings to an end demonstration of Walk3 program. Summary. In this presentation, it was demonstrated that when using Gazebo and ROS2, programming robot to walk becomes as easy as assigning values to the angle array elements. Angle values for robot joints can be determined by the trial and error method. Determining suitable angle values may require effort and time. 3 programs were developed in this presentation. Walk1 program provides great flexibility for the designing robot steps. Walk2 program offers simplified approach in which number of simulation steps is reduced. In Walk3 program, program part specifying robot walking sequence consists of less than a dozen lines of code. Those interested in programming robots to walk can use one of the programs offered to develop their own walking sequences easily.